3 feet of snow, solid, packed, unbroken, not a single track on the surface, not a single sound in the air. To every predator on Earth, this landscape is a wall. Prey is hidden, scent is buried, vision is useless. Every hawk has gone home, every fox has given up. Every human hunter would walk past this field and see nothing, but something is coming. A great gray owl glides silently over the snow. It doesn't circle, it doesn't hesitate, it doesn't look for tracks. It simply stops, hovers for exactly 3 seconds, and then drives both feet through 3 feet of solid snow and pulls out a living mouse from 3 feet below the surface, through solid snow, without seeing it, without smelling it, without any visible clue that the mouse was even there. Scientists who watched this happen for the first time didn't believe what they had just seen. They ran the experiment again, and again, and again. Every single time, the owl found the mouse. Today, we are going inside the greatest sensory mystery in the bird world. How does an owl hunt what it cannot see? What does it hear that no other creature on Earth can process? And why have scientists spent decades studying this bird and still cannot fully explain what happens in those 3 seconds before the strike? By the end of this video, you will understand something about sound, about silence, and about this extraordinary bird that will change the way you listen to the world around you. Let us start with what we know. Owls are nocturnal hunters. This is common knowledge, but common knowledge only tells half the story. Because the question that has fascinated researchers for decades is not whether owls can hunt at night. It is how precisely they can hunt. And the answer to that question is still not fully understood. In the 1960s, a researcher named Roger Payne at Cornell University decided to find out exactly how accurate owl hearing really was. He set up a completely dark room. No light, not even a single photon, absolute darkness. He placed a barn owl inside, and then he released a mouse. The mouse was wearing a small piece of tape on its tail that rustled slightly as it moved across dead leaves on the floor, in complete darkness. In a room where no vision was possible, the owl caught the mouse every single time. Payne was stunned. He removed the leaves. He made the floor completely silent. The owl stopped catching the mouse, not because it lost vision, it never had vision, but because it had lost the sound. The owl was not hunting by sight, it was hunting by sound alone, with an accuracy that made Payne's hands shake when he wrote up his results. Because what he calculated was that the barn owl could locate a sound source with an angular error of less than 1 degree. 1 degree in complete darkness from across a room. No instrument that existed in the 1960s could match that precision. Now here is where the science becomes genuinely extraordinary. Because the secret to the owl's impossible hearing is not actually in its ears. It is in its face. Look at an owl's face carefully. That flat, circular disc of feathers surrounding its eyes is not decorative. It is not for display. It is one of the most sophisticated sound collection devices ever studied by scientists. The facial disc functions like a satellite dish. Every feather is angled precisely. Every curve is shaped deliberately to collect sound waves from the environment and funnel them directly toward the owl's ears. Located on the sides of its skull, hidden beneath the feathers, invisible from the outside. And here is the part that makes engineers genuinely envious. The owl can adjust the shape of its facial disc. Tiny muscles beneath the feathers pull the disc wider or narrower, flatter or more curved, in response to the sounds it is hearing, essentially changing the shape of its satellite dish in real time to optimize reception for whatever sound it is currently tracking. No human technology does this. We build static receivers, fixed shapes. The owl builds a dynamic receiver, adjusting, responding, optimizing, continuously, automatically, while flying, while hunting, while calculating the exact position of something it will never see. But there is something else. Something that scientists discovered about owl hearing that initially seemed like a mistake, a defect, something that should have made hunting harder, but turned out to be the most important adaptation of all. Owl ears are not symmetrical. In most great gray owls and several other species, one ear is higher on the skull than the other. Not slightly higher, significantly higher. One ear sits above the midline of the skull, the other sits below it. This asymmetry means that the same sound reaches each ear at a fractionally different time and at a fractionally different volume. When a sound is coming from directly below, the lower ear receives it marginally louder. When a sound is coming from the left ear receives it marginally sooner. The owl's brain processes this difference, this tiny fractional difference in timing and volume between its two ears, and uses it to calculate the three-dimensional position of the sound source, not just left or right, but up or down, and crucially, how far below the surface. Scientists call this binaural processing. But what the owl does with it goes far beyond what any existing technology achieves, because the owl doesn't just calculate where the sound is coming from, it calculates where the sound source will be by the time it strikes, accounting for its own flight speed, accounting for the movement of the prey, accounting for the depth of the snow, all of this. In the 3 seconds, it hovers above the surface before it has ever touched the ground. Now we come back to those 3 seconds, the moment the owl hovers. To the human observer watching, nothing appears to be happening. The owl simply hangs in the air above the snow, still, focused, waiting. But inside those 3 seconds, the owl is performing a calculation so complex that scientists are still arguing about whether our current understanding of neuroscience can fully explain it. It is processing sound waves arriving at 2 asymmetric ears at slightly different times. It is filtering that information through a facial disc it is actively reshaping. It is calculating the 3-dimensional position of a moving target. It is accounting for the depth of 3 feet of snow. It is predicting the target's movement trajectory. It is calculating its own strike angle. And it is doing all of this, not with a supercomputer, not with years of training, but with a brain roughly the size of a walnut. In 3 seconds, researchers have attempted to model this process computationally, to build software that replicates what the owl does in those 3 seconds. The most sophisticated models they have built still cannot match the owl's accuracy, still cannot account for all the variables the owl processes simultaneously, still cannot explain exactly how the neural processing happens fast enough. The owl does something in 3 seconds that our most advanced technology cannot replicate, and it does it every night. In the dark, in the cold, under 3 feet of snow. If this is melting your brain right now, hit like so more people can discover this incredible story. But here is the part of this story where it stops being just about owls. Because scientists and engineers who studied owl hearing didn't just write academic papers, they tried to build things. And what they built changed the world in ways most people never connected back to this bird. The asymmetric ear principle that allows the owl to locate sounds in 3 dimensions directly inspired the design of modern sonar systems. The facial disc's ability to dynamically reshape itself to optimize sound collection inspired research into adaptive acoustic receivers used in submarine detection. The owl's ability to filter a single sound source from complex background noise contributed to noise cancellation technology now found in aircraft cockpits, hearing aids, and the earphones you may be wearing right now. Researchers studying how owl brains process binaural timing differences contributed to spatial audio processing technology used in everything from military targeting systems to the 3-dimensional sound you hear in movie theaters. One bird, hunting mice under snow, quietly reshaping human technology across decades, without anyone telling the story of how connected these things were. 3 feet of snow, a mouse hidden at the bottom, a brain the size of a walnut, 3 seconds, and a strike so precise that scientists still cannot fully model it. The great gray owl doesn't know it is extraordinary. It doesn't know that researchers have spent decades trying to understand it. It doesn't know that the technology in your earphones and your aircraft and your submarines carries a small piece of what it does every night. It simply flies out into the cold, listens to a world that is silent to everything else, and finds what is hidden every single time. Perhaps that is the most extraordinary thing of all. Not that this owl can do something science cannot explain, but that it has been doing it every night for millions of years, while the rest of the world walked past the snow and heard nothing. If this story changed the way you hear the world around you, subscribe to Birdhearts so you never miss another incredible bird mystery. And tell me in the comments, did you know owls could hunt through 3 feet of snow? Or did this completely blow your mind? I'll see you in the next one.